welcome. All right, everybody, welcome to CS10 Lecture 2. Today we're talking about 3D graphics, and the cool thing about that is it's awesome. Graphics are awesome. They're amazing. We're going to have so many cool visuals today and so many cool movies today. Hopefully you get really engaged. This engaged me. Every single lecture, we're going to have a technology. What I teach, I'll have a technology of the day. And so the new cool thing that's relevant to this lecture, I always try to find a technology that's relevant to the lecture, is that they have now, there was somebody threw down the gauntlet and said, can you render this image faster than, I think it was 50 seconds? And so somebody at Intel, which is really cool, some engineer working at Intel decided, I'm going to try to do that. So what they did was they cranked the speed, cranked the clock rate of their chip up, but that makes it really hot. So what they did was they had to super chill it. They cooled it down to minus 40 degrees Celsius to make it happen. And then they got to some 5 gigahertz, and it was really fast and screaming, going, but it was also being chilled down. You know, your laptop gets really hot when you run it? Well, imagine having to have so much cooling that you go to minus 40 to get that render. And that person actually had the fastest time, so that was kind of cool. So that's just the technology in the news about graphics, and they're trying to render that beautiful picture. And I'll even talk about the picture and why that's so cool and so important in graphics. So let me give you a sense of graphics from 10 miles up. And from this picture, it really should be 10 miles down. It's beautiful. So this is a rendering from a free renderer called Pavre. So graphics is one of the main research topics within computer science. Computer science has many research topics: AI, databases, theory. And graphics is right in there. It's one of the main subfields you can major in and get a PhD in computer science. So when we have computer science conferences, we say, hey, you're a computer scientist. Okay, special computer science handshake. And then the next question is, so what subfield are you? And you often say AI or graphics, and graphics is a very reasonable answer for that. One of our graphics group that I graduated from is ranked in the top 10 in the country, and we're really excited about that. In fact, we've just hired some new wonderful folks. Hopefully we're going to be ranked 1, 2, 3, or 4 in the next little bit, but we're top 10. We're really excited. If you hear graphics, you often hear 2D graphics, and 2D graphics are different from 3D graphics. 2D graphics are kind of sprite animation, Photoshop-y kind of things, graphic design, web design. All of that is not what we do. We do 3-dimensional graphics and kind of taking 3-dimensional scenes and rendering them in beautiful into 2D. And we'll talk about how to do that, which is really cool. So why do we care about them? Why do we even talk about them? Why is it even a field? Well, they're used everywhere. Nowadays, they're used everywhere. They're certainly used in film. They're used in TV. They're used in movies. They're used in film instead of movies. They're used in print. And they're used in video games. But they're different. Those two worlds are actually different. It's kind of interesting. And they have different needs. So in film, you care about the visual realism. You care about making this look as great as possible. And you can either have something that's all CG computer graphics, something that's all CG, like the Pixar films or the DreamWorks films, or something that has effects in it, like Transformers was a film that's filmed normally, right? There's actors running around, what they're running around from in real life is probably, what they've done nowadays is kind of a tennis ball with eyes. So the tennis ball with eyes on a stick. And some guys with a green stick and a green tennis ball, because you can remove green things from that plate very easily, they're going, and they're like, no, don't eat me, tennis ball man. And you have to act really well because there's nothing else there. You're looking at a tennis ball. And then they go back into post-production. You hand that to Digital Domain or Industrial Light and Magic, and then they add the amazing robot that goes, and the big soundtrack. And all of a sudden you feel like there's a real robot there, where in fact, in real life, in the movies, it was just a tennis ball. So the resolution we're talking about is hours per frame. You care about quality. This is going to be on the film. This is going to be archival. It's hours per frame. Critical, critical, critical. In a video game, you have an engine in your computer or your laptop or even your phone. Not so much your phone in terms of a specialized hardware, but you have video games, right? Let's talk about the main standard desktop computer. You have a video game engine. What does that mean? It means you have a graphics card. So there's typically a card that either comes with it or you buy special and pay a lot of money to have this special fancy graphics card that can render polygons, little triangles, sometimes squares, quadrilaterals, per second. You want something that's in the millions of polygons per second for your graphics card. The video game talks to your graphics card and sends its geometry, sends its elements of what the scene is, the car, the road, the house, and then the graphics card renders that into the picture. But the reality is, this is hours per frame, where you care about that being as good as possible. I don't care if this particular frame took 10 days, because that's the one we're going to ship around to be on posters and billboards the size of mountains. But this is part of an interactive experience, so the frame rate has to be really fast. So now we're talking on the order of 30 seconds a frame.
No.
30 seconds. Sorry, 30 frames a second. I flipped it. 30 frames a second. Hours per frame. Very different requirements. And so the challenge, here's the interesting thing. I have a friend who worked in the video game industry, and I'll talk about this next week, I believe. Same time next week. The challenge in the video game industry is how to make their algorithms, how to make the way they do things, the way they do rendering, to be of film quality, but at that insane rate. They have almost no time to do all that work to get it to look this good. I mean, look at this. You've got blur here, maybe motion blur, you've got depth of field, you've got a beautiful picture in the back of the Coliseum. To do this 30 times a second is incredible. So I really kind of honor the video game folks and the people who write graphics cards to be able to do that. It's a really incredible thing they do. So, very different things. They also have what we call pre-rendered cinematics. And a pre-rendered cinematic is like this. They go into the back room, they make a little short film, and then they'll insert that into it. So maybe you play the game and you're driving, and then you complete the level, and then they show you a little movie or a pre-rendered cinematic to take you to the next, as you drive your car away into the sunset. That might be a pre-rendered cinematic. And so the actual interesting thing is graphics cards are good enough nowadays, and the algorithms are good enough, that they no longer have to do that. It's as good. The in-game engine is as good as the pre-rendered cinematic. It's crazy. So spending more time and putting an hour per frame, they can get just about the same quality in real time, meaning 30 frames a second. That's incredible. So remember that I told you there's a big different line, right? There's a huge world of film and there's a huge world of video games, but that line is being blurred. And there's a challenge, it's kind of cool, I found this, to actually ask a video game team to take your engine and make a scene from a movie that looked as good as the real movie. And so this is the winner. I should probably turn these lights up because it's so beautiful. I want to make sure that...
Close the door.
Yeah, maybe I should close the door. This is a scene from what movie? Blade Runner. This is an amazing, amazing scene. Okay, there we go. Look at that. And it's just so gorgeous, and that is done at real-time frame rates, 30 frames a second. So, this guy is going flying away, and this looks so photorealistic, yet they're doing it 30 frames a second. It's incredible what they can do now. So I just wanted to say that the line is certainly getting blurred by the people who are working very hard on the video game side. So, let's talk about how it's done. Part of this lecture, this is one of the series of How It Works lectures, where we kind of try to reveal for you how things really work under the cover from the point of view of computer scientists. So this is this very, very, very high up, like 10-mile up simplification of the entire rendering, the entire process of going from zero, an idea, to a finished movie. And maybe I should turn a light up just a little bit for the film folks. Okay. So here are the four pieces: modeling, animation, lighting and shading, and then rendering. So quickly, modeling is making 3D models of things. And I'll talk about each one of these in detail, but just in general for the picture. Here's a picture from the Shutterbug rendering progression back in '91. This is like many, many years ago. Then animation, and here's a picture of a bouncing ball. And that's how you take your models and you move them. And you're still in 3D, by the way, right? So you're making your 3D models move. By the way, everybody should have handouts, so everything here you shouldn't be writing, because in theory, everything I've given you is here. Lighting and shading. You can't just have a model that has no surface. You have to work hard to get the alien skin and the dirt that's on my feet and my shoes and my thing. So you have to have, and the wood floor has to come from somewhere. And that can come from, so that's, we call that shading, and that can come from photographs, or that can come from writing programs to generate that, which is cool. And then the last stage is rendering. And rendering is the process of taking that 3D information now. Now you have all the things you need for your 3D world. By the way, the hidden thing I didn't mention is camera in here. You're also setting up your virtual camera. So you have a virtual camera, you have virtual objects, you have, each of those objects has some motion maybe, and you also have textures and shader properties on those things. And then you tell the renderer, go. And then you wait. If it's a video game, you wait a 30th of a second. If it's a film, then you might be waiting hours. Depends how fast your computer is, and you get this gorgeous picture with shadows and reflections and all of that. Okay? So now, clicker time. This is the fun part. Blank. What is the most critical piece to get right for a film? I'm going to open this because I think it's pretty hot. So now we go to this is the first clicker ever. A, B, C, D. By the way, you won't be graded on this. If you're here and you're voting, you get credit for being here, and you'll get full credit for that. We just care that you vote, not how you vote. I mean, you can care for yourself, but these are kind of questions in the middle, and you're not supposed to have the right answer for these lecture questions. Okay? So here's how this works. I say start, and now you start voting. You push, make sure you power your thing on, and just push A, B, C, or D. And you can change your vote. Okay? Is that kind of cool? And the number down here is how many people who voted. So 46 people. In theory, we have 90 people in the class. Not all 90 brought their clickers, but we should get somewhere upwards of more than 40, I would hope. By the way, we're giving these clickers to you for free with the hope that you'll return them at the end of the semester. You sign off a little thing, say, yes, I know I'm getting this clicker, and I promise to return it to you at the end of the semester. All right?
Jeopardy theme?
Sorry?
Jeopardy theme.
Yeah, the Jeopardy theme song. All right? So let's stop. We're kind of getting steady state here. I'm going to stop now. And what we typically do is something called peer instruction. And that is, you voted. Now I want you to turn to your neighbor and talk about it. And you are not just going to talk about it, you are going to convince your neighbor why what you said is right. So you, at the end of this discussion, have to have reached consensus, and you have to then hold your hands, sing Kumbaya, and vote the same vote. Okay? So, go. Turn to your neighbors, make sure you learn their names. Shake your hand, learn their names, and talk about this, the vote you just had.
I chose modeling. Because I think modeling, I think that modeling is kind of simple. I mean, it's critical to the general framework. For animation or for a
Okay, let's come back. Now you and your partner have to vote the same vote. So make sure you agree what you're voting, and you're going to vote the same thing. Remember, you don't get points off, right? It's okay. Go. Let's see how fast we can get to 50 votes.
I've never had an eye clicker before.
Neither have I. I was in chemistry for all 2 days.
All right, you got your clicker going in? All right, we'll stop at 50-ish. 51, all right. Hopefully we get
One
to
more
90.
question.
There are supposed to be 90 people in this class. Hopefully we'll get to 90. All right, here we go.
Yeah.
Stop.
right.
Here's the fun part, display. So, first thing to note is we only had A, B, C, and D. That's the first thing to note. And not for nothing, but this is being filmed, and you're Berkeley students, so some of you think that E is a valid thing. Not so good. Here we go. Better on the first try. So let's what have to happen. So A, B, C, or D, it's there. And almost an even distribution. And now here is, look how it changed a little bit. So D kicked up quite a bit. Interesting. And the right answer is animation.
Yeah!
Now the fun thing to do is at the end, what I'll try to do is keep track of who's been the most right, and we'll just see who's the most right over the course of the semester. Not for any points, but just we'll see what happens. Whoops. So hide that. Now let's talk about why is it animation? Well, you can have terrible modeling. You can have a 2D picture of a line. Nothing. No 3D, no models, no textures, no lights, no rendering. A line. And you can have an entertaining movie with a line. But if you don't have any emotion that's realistic, or not even realistic, that tells a story, then this can be amazing, and that's amazing, that's amazing. But if this is just dead, then you're not going to have a successful story. So that's pretty cool. All right. So let's talk about models. Let's now dig deep and get into each of the pieces. Isn't this fun? This is awesome, right? So let's get into each of the pieces. So modeling is where you decide what's going to be in your scene. You have to create objects. You have to create a set. You have to create hero characters. All of these things take a lot of work. But there are some tools that'll help you with that. So there are 3D scanners that'll let you scan an object. So if I'm just going to have this cup and it's not going to move, why have to spend the time trying to make a smooth surface and the thing on the edge? Put in one of these scanners, push a button, the thing comes out as geometry that I can use in my picture. That's awesome. So I'm going to show you a movie about that. How about that? So I have lots and lots of movies today to show. I hope I have time for them all. So let me get to the movie. I had it right here. CS10 lectures, graphics, movies, and let's go and see the whole body scanner and see if this is going to work for me. Give me some love. All right. And this is a promotional thing, so we won't have to watch the whole thing.
Has over 25 years of successful experience designing, manufacturing, and marketing 3D scanning systems for rapidly digitizing the human body. Professionals in numerous fields, including anthropology, medicine, art, entertainment, biomechanics,
Can I skip?
product design, and research rely on the quality of the measurements and color information captured by Cyberware 3D scanners. The Cyberware Whole Body X Color 3D scanner is economical, slightly, hands held
Get
away
to
from
the
the
key
body,
thing.
eyes open, facing
Here,
forward.
this is the cool part.
Scanning software
Okay.
and preparing for the scan. The subject stands on the platform,
This is
with
cool.
legs spread slightly, hands held away from the body, with eyes open, facing forward. The laser light used by the scanner poses no risk to humans.
Isn't that cool?
As the scan progresses, the subject should breathe normally and remain as still as possible.
Now, if this were Tron, you would disappear at the end of the process, right?
Then, once the scan is complete, the subject may exit from the scanner or remain there for further data acquisition.
Ta-da! That's what you get. And that's called a point.
Approximately 20 seconds after taking the scan, the data will appear in the scan window.
This is called a point cloud because all it's been doing is trying to gather all the surface points. And from this point cloud, what it can try to do is try to figure out if there's a way to kind of take 3 points and make a little triangle out of it. And then you can make a polygon cloud. That's really useful. But for here, it's just a point cloud. But they also have recovered color. And you're going to see, it's pretty detailed. You get some face stuff. You get, this is in grayscale. And there's a way to then add a color to it to get, essentially recover a character. But the problem with this is, that's the point cloud. The problem with that is significant. It's that if I want to then make this a character, now it's in my system, and I want to make it do this. Like from hands in the pocket, kind of hip, to da-da-da-da-da-da-da-da, doing a jumpy, I can't do that. Because I have not attached any animation parameter. It's just a cloud of points. It has no idea that if I want to move my arm up, that these points should move up. It has no idea. There's a lot more work to then actually take that and make it into a model that you can then articulate. Okay? That's just that's a little demo from the point cloud people. Stop that. Okay. So the other thing is interactive modeling. And interactive modeling is the process of using a modeler and using your mouse or a tablet and trying to create a 3D model from primitives and from shapes and from other things. And so I want to show you a little bit of a funny movie based on somebody having trouble with that. And this is called, this is actually here, it's called Cubic Tragedy. And essentially, some of the tools you'll see are tools that modelers actually use. This is a humorous movie, but it's the same thing, the same idea of what modelers do is what's done in this Cubic Tragedy. So look, you grab this, you extrude that square, now make a cube. This is what modelers do. Now you make a little slice here, and now you can adjust a piece of it, push it in, push this over, pull something up. This is what's happening right now is exactly how you make 3D models. You can pull, push, cut it, pull something out, push it back, scale it, all of that. So that's a little bit was exactly what modelers do. Let's just watch this little humorous film because it's a wonderful little film for you. So that's one of my favorite movies, little short films. But what they showed was a couple of the tools that interactive modelers use. You saw a couple things that take many vertices, the corner points on polyhedra, and make them into one. You can extrude it, a polygon and stretch it out. All those things that she was doing are things that interactive modelers do to kind of make a shape. You can go to a model library. People now do that a lot, and then they compile these libraries and then sell them. So you can actually go and buy models of trees and planes and all the things you probably want in your set. There's also procedural techniques. You can write a program. This is the cool thing that you're going to learn how to do in this class. You can write a program to generate geometry. And that's really amazing. So in this class, you'll write a program probably to draw something. But in theory, you could write a program to generate geometry, then be rendered in 3D. The same techniques you're using to draw your turtle around that you'll see, or your cat, you'll be doing to generate geometry if you take another graphics class. So, but once you make this model, you can't just say, I'm done. Just as the scanner wasn't done, you have to attach parameters that allow you to articulate that to then figure out if I'm all these polygons that make up a really detailed elbow, if I move maybe a skeleton, I'll define a skeleton, and if I move the skeleton, then the whole arm will move in a natural way. So I define kind of a hierarchical structure. So I move my shoulder, my hand should follow too. Not just my shoulder, my hand floating in space. It's all connected in this nice kind of skeleton way. So that's all things that's involved with that. Animation, the most critical part of any film, as I mentioned before. Many ways to make that happen. You can interactively keyframe, which means you take your articulated figure and you say, all right, I'm going to now go to pick up my glass. I'm going to say, all right, I should have had a V8 and pick up my glass. So I'd say here, and I freeze it. And I say, this is a frame. And then I move this thing to here and say, now that's a frame. And then move it down to here, it's a frame. And the computer can figure out the frames in the middle. It'll say here, and then interpolate to go bonk, and then down to here bonk. And so you only set 3 different poses, and the computer can interpolate that, and that's really important. So that's called interactive keyframing. We also have procedural motion. I can write a program, just as I can write a program to generate geometry, I can write a program to generate motion as well, and that's really cool. I can do motion capture, and that's what's seen here. People wear suits with glowing things, and they do some acting, and then they record that just as they're recording the shape, but in this case, they're just recording the skeleton. Because all they're doing is recording a knee, and an upper thigh, and an ankle, and then they're drawing a line between those two, saying the ankle's always going to be below the knee, and the knee's always connected to that. So the skeleton moves around, then you take that motion, apply it to the skeleton you've defined when you defined your model, and now you have your model move in a cool way, and they're showing here. They're showing a human does this, they recover these points, and now you're able to get a robot or a human figure or anything else mapped to that same motion. That's really cool. And they have motion libraries as well for that. You can also put physics into the system. That's really cool. You want to have something behave realistically? I just say, well, here's initial velocity. These things are hard surfaces that aren't moving, and then boom, 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 it'll all bounce around. It's really very cool. You can also have evolution come in and rule systems. I'll show you a movie about that, which is really cool. But the key thing is, this is where the emotions are conveyed, and that's what's so critical about that. That's why B was the right answer there. So let me show you the first cool movie I have, which is a friend of mine, Brian Merton, got a PhD here in our graphics group. And what he did was he built a system to allow you to have a very realistic physics. So if this cup were to fall, it would fall and bounce and then roll and handle all the frictional forces to make realistic motion. But what he did was he made a little movie. Here's a movie of a car taking these little weeble guys and knocking them off the plane. So that wasn't part of the thesis. The thesis was really the physics that makes this happen, and that was really powerful. But what he wrote, just for fun, which is incredible, is a set of rules of what the car should do. If you can't read it from the back, I can maybe zoom in for that here. And here's what it says. It's just a set of rules of what to do, right? It says, well, move forward. If the prey is near and dead ahead, then you're about to push it, which means keep going forward harder. Otherwise, if the prey is killed, then take the next guy and go back in here. If the prey is to the side of you, then spin and try to put it in front of you. So this is like a continual set of rules it's always doing to do its motion. And that's all it is. There are 5, it's like a baseball diamond. There are only 5 different things here, yet you get incredibly good motion based on just 5 simple rules. So let me now show you that movie, which I think is an incredible movie. Again, kind of a throwaway movie. It's like one small thing he did, but I think it's one of the coolest things in terms of motion. All he would set these rules up and he says, go. And all of this happens automatically from 5 rules. And these weebles have some rule state as well, and they're trying to run away and scramble. And it's now saying, okay, nothing in front of me, look up on my, what do I do? Well, look to the side, go find it, and push it, and push it, and push it. And now what you get is incredibly good motion because his physics engine really captures, you know, the dragging, the sliding forces, and the wheel forces. But it's really cool that you get all of this for free from 5 simple rules. He didn't say, well, you know, time step, go in the northwest corner, and then 10 seconds later, go to the center. He just said, do it automatically, like an artificially intelligent system. And that's the beginning of artificial intelligence, really. All it has is some rules and some states, and it just does it. It's pretty cool. And you can think of yourself having a similar set of rules. If I'm hungry, walk toward the nearest food, right? The same kind of thing. This is what it's doing. It's saying, I'm always wanted to push these guys be the king of the hill, so continue to do that until I'm the only guy left. It's pretty incredible. Yep, to the side, so back up, turn. All done automatically. It's really cool. And the nice thing about this, the nice thing about agents, the nice thing about kind of autonomous creatures is I haven't told it what to do. So I'm being surprised by a program. I run it and I have no idea what's going to happen, how they're going to run away in that clever way. So that's what I love about this work is that when you kind of lean into a rule-based motion, you have no idea what's going to happen. It's really very neat. You kind of set the rules up and maybe they all run to the wrong corners, maybe they do the wrong thing. It's kind of neat. So let me show you something else. So one of the most impressive piece of works I've ever seen in my life was this movie I'm going to show you here. Karl Sims is a foundational computer graphics researcher, and he created a system that will not only evolve using a genetic algorithm in which it says, I have some kind of a creature, and if it's winning the contest, then it gets to breed and make some copies, and they have some mutations there, and then I might have some randomness involved in that, and then I'll compete the children against that. And I keep doing that until I get some really, really very good behavior. So, This is called Evolved Virtual Creatures. It's an incredible piece of work. Let me show that to you now. And I think I have to run a thing called VLC to make that work here. Go and run VLC here and see if that works. Stop running that and play this. Oh, that's the wrong one. Sorry. Sims. I'm trying to drive the Sims to VLC. Okay, here we go. They sound. Yes, they should be.
This demonstration shows virtual creatures that were evolved to perform specific tasks in simulated physical environments. Swimming speed was used to determine survival. Most of the creatures are results from independent evolutions. Some developed strategies similar to those in real life. Once they're evolved, multiple copies of these creatures can be made and simulated together in the same environment. The next group of creatures were evolved for their ability to move on a simulated land environment with gravity and friction. Some simple solutions with just 2 parts were found. Some seemed like they could use some assistance, while others were fairly efficient, such as this rowing-like behavior. Here is an odd cousin of the previous. A mutation caused him to tumble. Some creatures evolved to incorporate contact sensors in their control systems. Here is another inchworm-like creature that tends to go in circles. This was actually a creature first evolved for its ability to swim in water, then later put on land and evolved further. A successful sidewinding ability resulted. Here is one with a hopping style. The protrusions on its arms seemed to help prevent it from tipping over. This was the fastest, with a successful galloping-like stride. This group was evolved for their jumping ability. This group was evolved for their ability to adaptively follow a red light source. The resulting creatures are now being interacted with. A user is moving the light source around as the creature behaves. This one seems to flail randomly, but somehow still manages to approach the light. Perhaps it is mean to move the goal away just as it arrives. Here is one that has propeller-like fins which are tilted depending on the direction of the light. It can adaptively swim up or down very well. This final group of creatures was evolved for their ability to compete for control of a green cube. The creature closest to the cube at the end of the simulation is the winner. Here, a strategy first arose for simply tumbling towards the cube. Then one learned to block out his opponent. But then later, one learned to overcome the obstacle by climbing over it. Some pinned down their opponents. Some covered the cube with protective arms. Others simply unfolded onto the cube. The success of a strategy is often highly dependent on the opponent. Here is a hockey-playing creature, which takes the cube away and wins by a large margin. Here are 2 similar hockey strategies battling it out with appropriate gestures. This crab-like creature walks well, but often continues past the cube and instead seems to prefer beating up on his opponent. Against the arm, the crab seems to simply walk away. A successful strategy is this 2-arm technique that swipes quickly in from the side and moves the cube over to a second arm. These are the final rounds of competition amongst the overall best. Finally, the seeker arm goes against the side swiper, but the cube is just out of reach.
Incredible, right?
That was made in 1994.
Yeah. This was all, so what he was evolving was the geometry and the control structure. So the control system that controls the animation. So it's not just how it looks, but how it behaves as well. All that at once were being genetically driven. It's really pretty powerful stuff. So I think that blew me away back in '94, and it still blows me away as some of the coolest work. All right, let's go to the next one, which is the next one of those 4 pieces is lighting and shading and camera, which I mentioned before. So you hire artists, just like you do in films, to set up lights in the scene, to make the scene appropriate. Let me add a middle light just for the camera. You then have teams of artists working on the shaders, and these are the people working on all of the surfaces that you have, and that often requires multiple layers. To make a banana look really like a banana, you have to have a bump layer for the outside, you have to have kind of reflection layer that reflects light. It's not just a banana picture that you wrap around. Most people think, oh, just take a picture of a banana and scan it and put it around a banana. It doesn't look like a banana. You have to have the light bounce in the right way for a banana to work. So it's really very cool that way. If you look at the coolest movie you've ever seen, I've seen, is Cars, in that it has, the cars themselves had this amazing paint, and cars in general have multiple layers of reflective paint that they have on them, and they have amazing glittery paint on some of the main characters in the Cars movie. Then you have a virtual 3D camera, and you're all set. That camera may then move over time. But then, rather than saying action, you say render, and that's the next step. So the basics of rendering, or the basics of 3D projection, are really, really easy, and they're grounded in high school geometry, okay? So for each frame, this is for each frame in the movie, you take the 3D geometry, you take the camera, you take what the surfaces are, and your goal is to figure out what is on one pixel. That's it. A pixel is a picture element. So I have a picture I'm rendering to maybe HD, that's about 2000 by about 1000, and for each of those pixels I have to figure out what color that is. Well, the math is that picture. You're basically projecting a 3D world onto a 2D plane. And so it's very much like what happens in an X-ray. What happens in an X-ray is, I'm a 3D object, here's X-rays coming over, they go through my body, and here's a film plane. So I'm projected onto a picture. Okay? So here's what happens here. You have an eye, here's your virtual camera, which usually draws an eye, and then here's a cube out there, and here's my film plane. I have to figure out what does it look like on my film plane. So let's look at the similar triangles and how cool this is. I know the distance to my film plane. I know the distance to my corner of my cube in 3D. I know how far over it is, so I know this big triangle, and I know this height of that small triangle. And I don't know is this guy. I don't know where that X is on my film plane. And this is just a top-down view. Obviously, I did this for the 2D picture, for a 3D image, but this itself is a projection of how that's happening into then 2D. So I have a ratio of bx, this leg over height equals big leg over big height, and I just can figure out what this missing distance is, or what that missing distance is here, based on the similar triangles. It's very, very easy. That's all the math that's involved. Isn't that cool? So essentially, that's how graphics works. That simple equation is that's the projection idea, and once you have that, you actually have all of it. So cool. There's some other rules for how light works and how light bounces off of things. We'll talk about it in a slide or two. And there are lots of algorithms to do this projection, to do this rendering. Okay. There's a phrase we use in our field called expensive. Oh, it's really expensive. Don't do that because that's really expensive. And expensive means it's going to take a lot of time, not money. Time. It's kind of cool. I don't have the time to wait 10 days per frame because I'm a video game, so I don't have time for that. So the real search is for photorealism. And there's a technique that we use in graphics called global illumination, which basically means trying to capture what all the photons in the world are doing. And it's really, really cool. So there are limitations. We certainly can't simulate all the photons. Right now, there are photons, I can't even count the number of photons in this room. And they're all bouncing around, they're all illuminating. And the reason that the bottom of this desk is light, even though no direct lights are seeing the bottom of the desk, is because all the photons are bouncing around and reflecting off the bottom and off my shoes and bouncing all around, right? So in the traditional way we used to do things, for many, many years, we didn't have global illumination because it was too slow. Computers were really too slow to do this until only a couple of years ago. And so we did something called direct illumination. Before I show you that, I want to show you a picture of the Cornell box. One of the questions, if we're searching for photorealism, then somebody has to have a brilliant idea saying, hey Dan, at the very least, if you're trying to get something that's photorealistic, aren't you going to build a real life scene and then try to image it with a virtual scene and make them match? And that's what they did at Cornell many, many years ago. They built a physical box. These are physical, cubes and rectangular solids with colors, and this is a mirror guy. And they built this. This is a physical, this This is the physical object. This is the photograph. This is the actual photograph of the actual 3D box that I could touch and poke and get my finger poked on. And there's a light source being blocked here. And then they said to the people in the computer graphics group, see if you can try to simulate that. So I said, oh, it's easy. Make a box. That's great modeling. That's 2 seconds. Bloop, box. Here's another box. Make that mirrored. Make that white. Put a light source. Adjust it. Go. It didn't look very good. And they worked very hard on their renderer, kind of the model of how they have light interact, to try to get that as close as possible. And this was very, very close. I mean, if you squinted your eyes, you can't tell the difference. It's really quite amazing. So they were doing very well. But one thing that's missing here are things that have different properties other than basically opaque matte surfaces like this and a mirrored thing. It's only 2 kind of surfaces in this picture, but in the world there are many other kind of surfaces. Like here's a mirrored picture, and here's a glass ball. And in very simple rendering algorithms, we call direct illumination algorithms, you don't get realism, meaning this is perfectly black, and this is perfectly black in the shadow. Well, light's going to go through this ball and get this and make this brighter than black. And light's going to reflect off of the red and the light here, and photons are going to bounce all around. That's never that black. Nothing is that black, because in real life, photons are bouncing around. So this is a very poor algorithm. So this is why global illumination is so great. Look how realistic that looks. That looks wonderful. Look, you have color bleeding. This guy's a little bit redder. This guy's a little bit lighter because they're near each other. Colors bleed in that way. Here you have light refracting through and forming a beautiful highlight over here, as well as doing something here. And you have, look, this shadow is very soft and beautiful. And you're used to soft shadows because the world is about soft shadows. So when you see a hard shadow, you think, oh, bad renderer, or not a global illumination renderer. It's probably a direct illumination renderer. If you have a soft shadow, that's what you want to have, because that's what happens in real life. And so that's a really great renderer, and thanks to Henrik Jensen at UCSD for borrowing these pictures. Almost done. So I want to share with you opportunities for you, and I'm exactly on time. Feel very good about that. I created a group called UC Bug in 2001 to basically make a mini Pixar. There were students that I had who wanted to learn how to make movies, animated short films, and they had no idea where to start. I said, why don't I create a group with no prerequisites? You can just walk in and I'll teach you how to use the tools, and I'll teach you how to make a story and take a story through modeling, through lighting, through rendering, until you actually have a final movie. And so we have done that. And so here's an example. 2002, we actually went back and saw the play, because it was the anniversary of the play from '82, and we decided to redo it in 3D. So I want to show you that movie really quick.
Memorial Stadium, 1982. With Stanford ahead, 2019, and only 4 seconds left on the clock, Cal would pull off the most memorable moment in college football history, the play.
Harmon will probably try to squib it, and he does. Ball comes loose, and the Bears have to get out of bounds. Rodgers along the sideline, another one. They're still in deep trouble at midfield. They tried to do a couple of... The ball is still loose as they get it to Rodgers. They give it back now to the 30. They're down to the 20. Oh, the band is out on the field!
But Stanford would never accept their defeat, claiming that Garner was down on the Cal 49. Thanks to advancements in 3D technology, we can resolve this dispute once and for all.
Harmon will probably try to squib it, and he does. Ball comes loose, and the Bears have to get out of bounds. Rodgers along the sideline, another one. They're still in deep trouble at midfield. They tried to do a couple of... The ball is still loose as they get it to Rodgers. They give it back now to the 30.
Takes out 3 defenders. Look at this. 1, 2, 3. That's the key to the whole play right there. 3 people.
The is out on the field. He's going to go into the end zone. The Bears have won. Oh my God! The most amazing, sensational, dramatic, heartrending, exciting, thrilling finish in the history of college football. California! The big game over Stanford!
And I don't know if you know some history. this is the final score on the books, 25-20. And when Stanford actually wins the axe, which happens every once in a while, they go back on the axe as a little history of all the victories, and they go back and change that date so that they actually win that game. It's pretty funny. So that's a little history there. So now, I'm interested in taking UC Bug as a statement, and I want to ask whether you strongly agree with that statement, mildly agree, neutral, mildly disagree, or strongly disagree with that statement. No prerequisites, a free course, 3 units, anybody on the whole campus can take this course. Go. How interested are you? Maybe. You're not committing to anything. Just kind of give me a query if that's interesting to you. We recently expanded that course from 30 students to 60 to be able to accommodate the campus need because there was so much interest in that. All right, stop at 50 and display. All right, look at this. 0 and 0. How about that? That's pretty cool, folks. So I do want to encourage you to think about that as a course for you in the coming semesters. So in summary, this beautiful picture. I love this picture. Beauty and joy of computing, are you kidding me? We got to start with 3D graphics. For me, that's what it was. That was all that was what got me so excited about computer science in general, is that this computer graphics that I could then get a PhD in. And the field itself has transformed the world. It's transformed all your entertainment, at least. Movies, games, print. How does it work? You've seen that already. I've explained the basics of it, and you now have the basics of how 3D graphics works. You can exercise the right and left parts of your brain, which hopefully this course is doing as well. And there are certainly opportunities for you at Cal to take the artistic side, UC Bug, or even the technical side in terms of taking a CS184, an upper division course in computer science. So, thank you very much. We'll see you guys next Wednesday. Have a great Labor Day. Woo!